Hello, my name is Alina Kindratenko, and I'm a Senior Education and Outreach Coordinator at the National Center for Supercomputing Applications. And CSA has a history of nurturing innovative concepts, and some of the best ideas have come from highly motivated, creative undergraduate students. And CSA's Students Pushing Innovation Internship program was created in 2012 to provide University of Illinois undergraduates with the opportunity to participate in the center's interdisciplinary research efforts in many areas, including digital agriculture, bio and health sciences, earth and environment, astronomy, and many more. SPIN provides more than paid internships, but also opportunity to work alongside with the world-class and CSA researchers, staff, and faculty affiliates, and meaningfully contribute to cutting-edge projects, extend their professional network, and even find new friends. SPIN interns have an opportunity to be recognized with NCSA's Fiedler Innovation Undergraduate Fellowship Award for outstanding interdisciplinary contributions to their SPIN projects. This award is part of a $2 million endowment from Jerry Fiedler and Melissa Alden to the University of Illinois in support to the Emerging Digital Research and Education in Arts Media Institute, which is based at NCSA. Today's SPIN intern presentations will range from analyzing satellite data for agriculture, for example, predicting grass waterway using Champaign County satellite data, to multi-scale modeling of sterols in the membranes environment, to weighing black holes with machine learning, to visualizing materials using virtual reality. Thank you for joining us.
Hello, my name is John. I'm a SPIN intern here. And before I start talking about my project, I just want to thank the SPIN program for giving me an opportunity to work on it. And also my mentors, Caillou and Sean Ya, for helping me out with the process. So the goal of my project is given an image of crops taken below the crop, so looking upwards with the sky as the background. We want to segment out each pixel, whether it's plant or sky. You can see an example on the bottom where the left is the input image of the crops, and then the right is the output like mask of where white is plant and black is sky. And so the reason for this is once we have this segmentation, we can use it to find the percentage of each image, which is plant. And when we have that for different images from different places around a crop field, we can use it to find the leaf area of that field. And then that's useful for a couple different types of agricultural analysis. So for this project, I decided to use the UNet neural network, which is a type of machine learning model often used in segmentation problems. It was first used in segmenting out different cells and biomedical images, but it also works well for this type of problem. So once I had the model, I needed a set of images to train the model on. So I found 229 original images, which were like the images on the left of crops. And then I manually created 229 of the images on the right, the binary masks and then so the way that this works to the model is you feed the input, like normal left RGB image, as the input to the model, and then you feed it the right black and white output mask as the answer to the model. And then the goal is to teach the model, given an input image, this is what the answer should look like. And so then when we later feed it different types of or different input images, it can correctly find the correct output. And then these 229 images isn't enough. I augmented them by either flipping them or brightening or darkening them to get a final set of 916 images to train the image model on. And then I resized each image to be the same size because the model performs better when they're all the same size. So after training the model on all these images, I then used it to predict a set of 25 set validation images and found about a 97% accuracy, correctly predicting each pixel. So here you can see some examples where the model did not perform that well. So like the blurry leaves on the top left, and then the dark blurry leaf on the top right of the right image. The model missed both of those. The model tends to perform worse on like dark or blurry or cloudy images, but it still performs pretty well on most images. And then here you can see some images where the model performed correctly. And then obviously there's a lot more images. I just couldn't show them all. So I'm mostly finished with this part of the project. And then the next part is working on the same type of thing, but for downward facing images where the dirt is the background. So this is a lot more difficult because sky is very different from plant. It's almost always blue, whereas dirt is a lot more similar to plant. So it's a lot harder to segment, but I'm excited to start working on that next. Thank you and bye.
Hi, everyone. My name is Yihong, and I'm a spin intern working with group mass crop monitoring using satellite data with mentors Professor Kai and Dr. Bin. Today, I'm going to go through a project which is grass waterway prediction that aims to identify the grasslands along waterways through a satellite image. First of all, I will go through our data and the pre-process we performed on the dataset. We picked a 3-meter resolution surface reflectance image from Planet Lab. However, this data is very inconsistent between sources because Planet Lab uses different sensors and satellites to capture these images. Therefore, we performed a normalization, which is the CD cumulative distribution matching with the stereo fusion dataset, which are more consistent and are more reliable. Finally, it's worth to note that this demo is created on images of Champaign County on May 9th, 2020. For the methodology we picked for this project, we use traditional computer vision methods, starting with calculating normalized difference vegetation index, which gives predictions on areas covered by forest and vegetations. Then we use CDL and CLU to remove uninterested areas. Since CDL and CLU provide pixel-wise label for ground type, it can effectively remove areas such as roads, cities, and hunts, which are not interested. After that, we performed some image denoising methods, such as morphology and running a sliding window through the entire image to remove noise and overly dense predictions. Finally, we use the USGS streamline data to connect each component of our predictions and use a connected component analysis to remove the sparse predictions. And this is the result of our project. On the left-hand side, you can see the raw image data. And on the center, you can see the raw scores of normalized difference vegetation index. As you can see, without our post-processing pipeline, there will be a lot of extra predictions, especially on the top, the city areas on the top right, and the roads along the fields. On the right-hand side, you can see through our pipeline that most of these uninterested areas has been cleaned, and we retrieved a relatively good prediction result. And that's all I have to say. Thank you very much for tuning in.
Hello, my name is Trevor Wong. I'm an intern at the National Center for Supercomputing Applications, and I'm currently a sophomore pursuing a degree in computer engineering. I'm work as part of Caillou's lab. The larger research focus of the lab is using satellite data for large-scale crop monitoring, and the project I've been working on specifically is using satellite data for cover crop detection. So just some background info. Cover crops are crops that aren't intended to be harvested. So these crops can reduce erosion, fertilize the ground, and these crops are often grown off-season, especially in the winter. So tracking cover crop usage at a large scale provides us with a lot of useful data for future research, such as the how using cover crop influences crop yield, and then also the popularity of cover crops in various environments. So using cover crops is a common practice in Illinois and in surrounding states. So in terms of methods, we use the crop data layer to generate these statistics on a field level, so to figure out where the fields actually are. And then we use what's called normalized difference vegetation index, which is essentially a measure of how much vegetation growth there is in a different area to guess whether a field is using cover crops. So we kind of draw a line where most of the growth occurs that represents the actual crop. And then we find the area between the actual NDVI and our linear regression model. And if there's a lot of area, that indicates there's a cover crop because it means there's something growing other than the main crop. So you can see an example plot of that on the bottom right here. And on the top right is an example of a crop data layer showing corn and soybean. So some results, we came up with a threshold because we have county level statistics, or we can approximate a threshold for what area under the NDVI corresponds to whether or not a cover crop is being used. And as you can see on the map and in the graphs below, we found there's correlation between geographic location and this threshold value. So in future research, perhaps we can use climate metrics to predict this threshold value and thus be able to predict whether or not cover crops are being used, even for other states than Illinois when we don't even have a ground truth.
Hi, my name is Sneh Pandya, and this is my project, Weighing Black Holes with Machine Learning. So in this project, we're using machine learning methods to estimate the mass of supermassive black holes. So supermassive black holes are contained in objects known as active galactic nuclei, which are understood to be the most compact luminous objects in the universe. And the luminosity of these objects is understood to be caused by the accretion of hot matter as it falls onto supermassive black holes. So these black holes typically have masses greater than 1 million solar masses, so very large. And measuring the supermassive black hole mass is important for understanding the formation and evolution of AGN. So black holes in general form when matter achieves critical density in space. So you basically have too much stuff in too little space. And what this does is create a singularity. And this singularity creates a gravitational field so strong that not even light can escape. So this image here on the left is the Event Horizon Telescope image of the black hole at the center of galaxy M87. And this was actually the first direct observational evidence for black holes. So the data we use to estimate these black holes are light curves. And so light curves are single epoch spectra, and these are cheaper data than what's traditionally required to weigh black holes. So traditional methods would require full atomic spectra and data from several catalogs. And the important thing to know here is that that data is more expensive and more tedious to gather than light curves. The reason we want to use cheaper and more efficient data is because in the era of the Vera Rubin Observatory, this very large upcoming survey, we're going to have an estimated greater than 10 million possible AGN candidates. So this just calls for a much more efficient and cheaper approach to weigh all these black holes. So neural networks are exceptionally well at deciphering nonlinear encoding in data and complex data sets. So that's why we use neural networks, specifically feed-forward neural networks in our case. And what we do in addition to the feed-forward neural networks is an extensive amount of data pre-processing to basically give our data a push in the right direction for our black hole mass estimates. And in the past, we've considered more complex neural network architectures, notably ResNets and Google Efficient Nets, as well as traditional machine learning means. And we've sort of arrived at feed-forward neural networks at the moment as being the state of the art. And so here's just a quick recap of our results. I invite you to check our full publication at arXiv. This paper was accepted to the Machine Learning and Physical Sciences Conference at NeurIPS 2020. But on the left here are results for AGN redshift, and redshift is basically a metric for quantifying how far away and how old our black hole is. So you can see our redshift results are really linear, really good. And on the right here, results for mass. We do have a bit more scatter in our results for mass, but the important thing to realize here is that our uncertainty in our prediction is almost equivalent to the uncertainty in our ground truth itself. So this is really big. It means that there's definitely a physical relationship between our light curves and our mass. And yeah, that's our project. I invite you to check out our paper, and thank you so much.
Hello, my name is Mohammed Jamil. I'm a spin intern at the National Center for Supercomputing Applications. My project involves automatically testing the Einstein Toolkit using GitHub. My mentor is Roland Haas. So first, what is the Einstein Toolkit? It's a set of tools designed to research astrophysics, gravitational physics, usually involving black holes and stars. It contains components of another toolkit, which is called Cactus, which does computation of very powerful computers. So whenever a change is made to the Einstein Toolkit, the updates are tested via a Jenkins server, which is a continuous integration service. I'll explain what that is in the next slide. The toolkit contains 270 modules and 327 tests, which are developed by different developers from different universities. It currently has 310 registered users who use it for their own research purposes. So what is continuous integration? It's a development practice that involves repeatedly updating code in a repository. And it's built and tested to find errors during development. And so you can use the data you get from the test to find the bugs and make reports from them. And GitHub Actions and Jenkins provide services like this. The current beta version of the Einstein Toolkit uses Jenkins, but my goal is to make it use Einstein Toolkit as well. So my goals were to make the test run on GitHub Actions and then display helpful data, some that were not present on Jenkins already, and then also keep all the existing functions that were on Jenkins on GitHub. And so I also added additional functionality that wasn't present before, and that makes them more helpful. And the final step would be to have it receive live updates and do the test multiple times for each update. So far my progress is that I have a web page that's generated after someone updates the Einstein Toolkit. And so it generates a report showing the summary data. It stores files that will be useful, like logs. And so developers can access those logs to debug and find problems. And then there are plots to show which tests failed, which tests didn't fail. And then it also shows if anything happened during the building process of the Einstein Toolkit. And those warnings help locate which parts of it could have problems. The plots are interactive, so each of the points on the plot would lead to previous versions, so they can find what changed between versions. And that's all for my presentation.
Hey everyone, my name is Jitin Mantraman, and this semester I work with NCSA SPIN mentors, Dr. Holzer and Dr. Zhu, to study the impact of diet on the human gastrointestinal microbiome. Let's get started. First, a bit of background on the human gastrointestinal or gut microbiome. Thousands of microbial species reside inside your gut, and these microbes are linked with various biological systems in your body. For example, the content of your microbiome can influence your mental health, your immune system, your tendency to put on fat, and various other bodily functions. Luckily for us, we know that the microbiome can vary even on a daily basis, and we can modulate its composition through drugs, hormones, and food. So our study is focused on how food can impact the gut microbiome. We looked at a handful of whole foods to see if we could develop biomarkers of their consumption. For example, we'd be interested to know exactly how avocados impact the microbiome, and if we could identify someone who ate avocado compared to someone who didn't based on the contents of their microbiome. We collected various data from the study participants. This included the DNA sequences of the actual microbiomes in their gut, as well as their fecal metabolites. For this talk, we'll focus on the metabolomic data. Metabolomic analysis involves using GCMS to identify which metabolites are present in the subject's fecal matter and in what quantity. All of the byproducts of the microbes in your gut end up in the fecal matter. So this is a useful way to develop a downstream view of what your microbiome is doing and how a specific food may be affected. Our dataset includes about 300 different compounds that were produced by these microbes. For example, linoleic acid was one of the compounds that we had in our dataset. Using machine learning techniques, we were able to build sparse linear models that could correlate very accurately separate subjects into treatment or control groups based on their metabolites. For example, in the figure on the left, we see that our model could identify whether or not a subject consumed almond with 93% accuracy. On the right, we can see that the model does not need to rely on all 300 compounds, but was able to identify biomarkers specific to almond consumption. In this case, 2 carbon chains along with glycerol are sufficient to figure out if a subject has consumed almond. In conclusion, we found that whole food intake significantly impacts the composition of the gut microbiome and therefore the metabolites. It's also possible to identify which specific metabolites a food influences. This is very useful as we can apply this knowledge in various settings. For example, providing targeted advice for health issues to patients based on the microbiome, as well as verifying when study participants follow protocol. One question we were left with was why some foods are easier to identify compared to others. There are many factors that could be involved with this, and our hope is to explore this line of questioning in the future. And that's all. Thanks again to my NCSA SPIN mentors and the program as a whole, and these are a list of references. Thank you very much.
Hello everyone, my name is Matthew Jin, and I'm currently a sophomore majoring in computer engineering. My project is called The Use of Natural Language Processing Methods to Parse Birth and Death Records. My mentors for this project are Dr. Madhav Erdogan and Dr. Zoroastrian. So the goal of this project is to investigate health disparities arising from birth and death outcomes that exist across the residents of Champaign County through parsing and analyzing electronic birth and death records from the last decade. In particular, we're focusing on identifying maternal health disparities and how these disparities are associated with various birth outcomes. So in this project, we develop a Python pipeline for digitizing birth and death records with optical character recognition, specifically PyTesseract. This research should provide an autonomous tool for future projects, which require the parsing of not only birth and death records, but also other records in medicine. So to briefly explain how the pipeline works, we receive real birth certificate data in PDF form from the Champaign-Urbana Public Health District. These PDF files are hand-scanned and imperfect, and as a result, we have to use optical character recognition to convert these files into image files, and then convert these image files into text files. Here's what we ultimately see in our text file. With these text files, we create a CSV database of the patient data extracted from these files, from these text files. Parse through the text files and match desired expressions. I'm currently using regex and NLTK in Python. Later, I'll talk about the project's use of the open source computer vision library. Here are some of the images of our current database. So the row index is each patient file name, and the column index is all the fields in the birth certificate data. On this slide, you can see in this snippet of the table that the pipeline has almost successfully extracted fields 21, 22, and 23 in the birth certificate file for patient 15. On our next slide, the image shows that the pipeline has extracted the time of birth, sex of the baby, date of birth, facility name, and the date of birth of the mother from 5 different patients. However, as you can see, there is a missing value in this snippet of the table. So to fix this issue, I've looked into using very simple computer vision and PyTesseract's image to data function. With these two tools, we are able to essentially zoom in on different regions of the document to reveal more accurate recognition of characters. Here is what that looks like. So in this example, we are trying to extract a missing value for the sex of the baby. The pipeline will first search the image for the word sex. After it has found the word, the program now has the coordinates of this word and also the width and the height of the word. With this data, the code will essentially zoom in on this region of the image to allow for OCR to have a closer look at what it initially missed. As a result, the resulting text is much cleaner, and now we see that the sex of the baby is female. So where do we go from now? I'll use OpenCV to improve the pipeline so that there aren't any missing fields or values. After we extract almost all important data, medical data from both the mother and the infant, then we can start analyzing and relating different fields of interest with machine learning to find significant health disparities. To end, I would like to thank my mentors, Zainab and Justina, for supporting me throughout this project. And most importantly, I'd like to thank the NCSA SPIN program for making this opportunity possible. And yeah, that was the end of my presentation. Thank you for listening.
Hello all, my name is Soumya Agrawal. I'm a SPIN intern. I've been a SPIN intern for about 8 months. My research is basically concerned with discovering biomarkers for coronary microvascular disease. My mentors are Zeynep Madakar-Dokan, Justina Zaraskin, and Alicia Igor-Dando, and my affiliations are with the NCSA and SPIN program, and I'm very grateful to them. The term biomarker refers to a broad subcategory of medical science, that is, objective indications of medical state observed from outside the patient, which can be measured accurately and reproducibly. Coronary microvascular disease is a heart disease that affects the walls and inner lining of tiny coronary artery blood vessels that branch off from the larger coronary arteries. This is basically, biomarkers are anything from metabolites to blood pressure, which can indicate a certain disease. And the disease that we're focused on is coronary microvascular disease. This disease predominantly affects women. And if we find biomarkers for it, then identifying it in patients when they come into the ER will be a lot faster. And any other way, it'll be a lot faster to identify it. In the summer and fall of 2020, I basically performed pre-processing on the data and found the biomarkers. We had about 70 patients and over 410 variables, which were cleaned, imputed, organized, and normalized after which we performed the t-tests on two groups. We created a group of CMD patients and non-CMD patients. And from all the variables, if you find a t-test and see which variables had significant differences for the CMD group. And then we used machine learning to verify these models, which was decision tree algorithms, logistic regression, and random forest approach. Out of that, we found the logistic regression model was the most fitting one because of cross-validation. And the same process was applied in the fall 2020 when we got some more variables. And finally, we have a set of about 67 robust biomarkers which now need to be verified. So this semester, my focus is primarily to visually represent this research. To increase my perceptive analysis. So we're going to be working with ROC curves, heat maps, and PCA charts. In the last 2 weeks, I've been finalizing my work on the heat maps. So on the right side, you can see there's a random like pictorially like a heat map shown. Or on the left side, there's an ascending order in which the heat maps are shown. So it's more easily for someone who understands the biology to see which pattern actually makes sense. Finally, I would like to thank the NCSA and the SPIN program for this opportunity. I would like to thank Lena for all that she does, and I would like to thank my mentors. Thank you.
Hello, my name is Andy Sima. I'm a senior studying environmental science and creative writing. I've been a SPIN intern since the summer of 2020, and since the fall of 2020, I've been working on a project about COVID-19 biomarker data and machine learning. I have undertaken this project with Dr. Madak Erdogan as my mentor. You may be wondering, what is a biomarker? A biomarker is any sort of measurable indicator in the body. For example, biomarkers can be used to determine the presence or likelihood of diseases. In the case of my project, my dataset uses protein biomarkers found in the bloodstream. By analyzing these biomarkers, we can hope to determine proteins associated with the risk of COVID-19, individual proteins associated with the infection itself, signs of previous infections, or even symptom severity. The possibility for studies based on biomarker presences or absences is large, especially since my dataset also includes time data, allowing for studying changes in the biomarkers. The dataset that I am working with comes from the data collected during the summer and fall of 2020 from the Massachusetts General Hospital. The data of over 1,400 protein levels comes from 384 patients, 306 of which were COVID positive, and 78 of which were COVID negative control patients. This data is available publicly and for free. It includes patients 18 years and older with severe symptoms and samples taken on days 0, 3, and 7 of their stays in the hospital. Our goal is to use machine learning models to classify this data and determine what biomarkers are found to be significant, or possibly what changes in biomarkers may be significant. Machine learning is a technique in which a computer algorithm is fed sample data or pre-classified test cases, and then, using that data, builds a model to predict the outcome of new unclassified data sets. It's like giving a computer a bunch of pictures, telling them what they are, and then the computer teaches itself to identify new pictures. There are tons of different variations, but my machine learning model for testing this biomarker data runs in Python with Python packages like scikit and keras, using random forest models, Pearson scores, LSTM models, and others. Hopefully, with these machine learning techniques, we can determine important biomarkers related to COVID-19 and help in the fight to slowing the pandemic. Thank you.
Hello, my project is dedicated to researching the multi-scale modeling of sterols in the membrane environment. So my name is Andrew Lee, and I am currently a sophomore here majoring in chemistry and planning on minoring in computer science. I'm currently working with my mentor Taras Pogorelov alongside the NCSA SPIN program to research this project. I am specifically studying the sterol ergosterol and have been studying its dynamics in the membrane by utilizing various approaches. Sterols are a type of lipid and a subgroup of steroids. Ergosterol is a type of sterol found in fungi, and its main function is to regulate the membrane fluidity and its biological processes. Cholesterol, on the other hand, is present in higher eukaryotes such as animals and humans and assists with maintaining its cell membrane. As of now, we do not have inadequate knowledge as to the exact dynamics of sterols in the membrane environment, so I'm working to learn more of that. And then here's the methodology and all the programs that I have been used to assist with my research. I use CharmGUI to help build the membrane systems, use NAMD to run the replicates, Gaussian to run the chemical shifts, DXC to run the MD, and RStudio for the analysis. The main purpose for why I'm studying ergosterol is to better understand the antifungal drug amphotericin B. So for over 50 years now, amphotericin has been used as the last line of defense to treat life-threatening fungal infections in humans. It's often called the last drug of last resort, specifically because it is very toxic and powerful for humans to handle. It exists as large extramembranous aggregates that kills the yeast cells by extracting cholesterol located in the lipid bilayers. Amphotericin can also extract cholesterol, which is what makes it deadly for humans. So as you can see from the two figures, the top just shows the molecular structures of both amphotericin B and ergosterol. The bottom shows the two and its interactions with each other. The bottom figure shows the amphotericin sponge and how it has already extracted the sterols. So pretty much if there was a before and after figure for this, the before image would show the ergosterol between the lipid bilayers, which is the gray, and then the after image would be this, where the amphotericin is working on extracting the ergosterol to create this big sponge. On this slide is an MD model of ergosterol in the membrane. The top right depicts the chemical structure of the POPC, and the bottom shows the chemical structures of ergosterol. So for this experiment, we replicated 10 models of ergosterol at 293 Kelvin, made 30 ergosterol per membrane, 100 POPC per membrane, and then ran it at 100 nanoseconds. So for this slide, we are looking at the chemical shift of ergosterol, and what this does is it pretty much gives us a better idea of the geometry and environment of ergosterol. So top picture describes the differences in chemical shifts between the MD and experimental ensembles. So there are 28 carbon atoms in ergosterol, and all their chemical shifts were calculated. The pattern goes to show that both the computational and experimental values both rise and fall together, which indicate that our data was similar to that of the experimental. The bottom figure displays the difference in chemical shift values. So for the computational values, we subtracted that from the experimental values, which is what is shown. Now, if you look a little closer, it can be seen that the majority of the carbon atoms, the difference lies between 2 ppm, which goes to show that our data is in agreement and helps us better understand their ergosterol's interaction with amphotericin B. For the next step, I'm going to work on calculating the MD order parameters, cross-correlation analysis, and radial distribution functional analysis to better understand ergosterol's interactions with amphotericin B. Thank you.
Hi, I'm Justin, and this year I was tasked with solving financial inverse problems with physically inspired neural networks. The inverse problem in the sciences is pretty common, and the gist of it is to find causal patterns given the effects that we can observe. One example is source reconstruction in acoustics. In finance, it's similar in that we take things that we can observe, such as stock prices, and we're trying to solve for things that we can't observe, such as market volatility. The importance of this problem extends to finding liquidity in the market and identifying risk for people and shareholders. And then finally, we hope that our work can be expanded to solve inverse problems in many more complex fields that aren't just finance. Because the way that we currently do it is pretty generalized and can be easily changed to something completely different. So physically inspired neural networks are a family of neural networks that are regularized through partial differential equation systems. Mainly the reason why we need this is because purely data-driven machine learning models are a little bit too black box for solving inverse problems, in that there's too much freedom in the parameters. So there are multiple correct solutions. And when we're trying to solve for an inverse problem, there needs to be sort of one correct solution, because we would hope that given a specific cause, we get a specific effect. Then partial differential equations, on the other hand, are very hard to solve, and they're also very rigid with their assumptions. And because of that, they're also very non-adaptive. So we combine both of these to sort of leverage the strength of both to create a neural network, or sorry, a partial differential system that's also adaptable. So the idea of how they work is actually pretty simple, ignoring a lot of this math. Basically, we define some neural network and we say that this neural network is the solution to a partial differential equation solution. We then define our loss function as the difference between our observations as the output of the neural network, along with the partial differential equation itself. That way, the partial differential equation is forced to be solved, as well as doing it for the specific values we observe. And then our goal is to sort of find more physical demands to increase regularization. And so our current results, the thing we're working with right now is the famous Black-Scholes equation. So as you can see here, these are some graphs of the predicted and the actual. So on the top left, we can see that the results are almost perfect for the model. The problem is we're trying to sort of also solve it for these intermediates, so sort of the inverse. So the challenges we face is discretization and then on a bigger level, sensitivity and conditioning on inverse coefficients. So we want to sort of be able to bound our error on inverse coefficients given an error from our observations. So then this leads to sort of freedom in any error ball. So given that we can bound our error to some epsilon, how do we bound error to our derivatives, or how do we bound error to the inverse coefficient we're trying to solve for? So this is sort of what we're working on, because currently there's no theoretical basis for this at all. And we hope to be able to then well condition this problem and extend it to other fields. Thank you.
Hi, I'm Zili, here to present the virtual reality app I worked on under Professor Schleffer. In this presentation, I'll use both the first-person view and the third-person view to demonstrate the features we have. When you enter the app, you'll see this menu screen. When you click on one of the buttons, and an atomic structure would show up. As you can see, there's a menu bar above each model. The models are loaded with a bounding box by default, so you can easily drag it, resize it, or rotate to a specific angle. It gives you several options. One of them is to disable the bounding box that's around the model. You can hover above the specific atoms to see their names. You can also add a plane, and as you rotate the model, the plane would follow. This allows you to enable cross-section view, which lets the app only render one side of the plane. So when you rotate the model to turn it around, you can see how the cross-section would look like. You'll be able to see the atoms inside. You can switch to isosurfaces. When you click on one of them, you'll be able to see the electron density of these structures shown through isosurfaces. For these models, you'll be able to adjust two parameters. The slider on the right lets you change the atom radius, and the slider on the right lets you change these isosurface levels, so you'll be able to see another level of electron density, and when you release the button, the model will be re-rendered. The app can also handle much more complex models. Here, for instance, this model has hundreds of megabytes of data. You can see that it takes a while to load in, and when you adjust the parameter, it may take a second for it to apply. But other than that, you should receive no frame drops. If you have a VR headset and would like to try it out yourself, you can go to Professor Schleffer's website to download the executable. Thank you for your time and stay safe.
Hi, my name is Ruby Wang, and I have been working on the Champaign County 2-on-1 reboot project under the provision of Dr. Nita Chen, Jorge Alvarez, and Mitch Oliver for the past academic year. I will do a brief introduction about our project, and we welcome anyone who is interested in our research work to contact us. So what is 2-on-1? 2-on-1 is a hotline serves to non-emergency community information and referral services providing. It offers referrals to basic human needs resources, disaster response and recovery, health resources, employment supports, transportation assistance, education programs, disability services, children, youth, and family support, volunteer opportunities, and donations. Why do we need 2-on-1? Even as a developed country, the poverty rate in the US is extremely high. Many people live on community supports and resources. However, how to manage these useful resources inside of community is a problem. Most of the time, people do not know about the services provided by the community. 2-on-1 as a 24/7 hotline is designed for resolving this kind of issue. Our project aims to provide more available options for the communities to access these services information, collaborating with Champaign County Mental Health Board, Cunningham Township, HAS 2-on-1 Bloomington, Community Data Clinic, and UIUC NCSA. We intend to create a platform that is more user-friendly and build connections between users and service providers. Here are some recent goals that we have been working on, including redefining user groups by working closely with Champaign County community and hear from local users, running a new responsive platform, re-improving old features to be more efficient, and creating new features. We intend to narrow down the gap between users and service providers. We also came up with great ideas inside of our team from service providers, integrated user needs, things like service shopping cart, optimized searching algorithm, chatbot, and many other ideas that we would like to test out and bring towards community services like 211. If you're interested in our research, either participating or looking for more information, please feel free to reach out to us. Thank you for listening to my presentation and have a nice day.
Hello, my name is Ishani Desai. I'm a junior studying stats and CS in the College of Liberal Arts and Sciences at the University of Illinois. Before we begin, I'd like to credit Elena Kindratenko, my mentors Loretta Avil and Kingsley Osiah-Siwe, NCSA, and the SPIN program for giving me the opportunity to work on the Athletic Data Analysis project. Our project revolves around frequent pattern analysis and rule association. A frequent pattern is a conjunction of features that occur together often in a dataset. Association rules are if-then statements generated from frequent patterns, where the antecedent and consequent are each a set of features. The goal of our project is to use frequent pattern analysis and rule association to find tendencies in an opposing football team's play calling to help plan for Illini football games. We start off with datasets consisting of roughly 180 features that describe each play in the game, such as down, players involved, pass completion, etc., and we often analyzed 4 or more games. Many of our features have complex values, so the first major step of our process is to expand these complex feature values into binary features. After expansion, we end up with around 2,400 features. Here's a process chart detailing what happens after feature expansion. From an expanded version of our initial data, we generate maximal frequent item sets, and then move into a process where we remove item sets with dependent features and instead check if any of their subsets are valid. The reason for this last step is because real-world data almost always has features that are dependent, while available algorithms assume feature independence. In order to account for this, we filter out rules with dependent features. From a dataset consisting of relevant plays from 4 games, we end up with thousands of valid frequent item sets. We then generate association rules from these frequent item sets. We filter these rules based on metrics such as support and confidence. From the patterns we mentioned earlier, generated from 4 games, we end up with a total of 5,000 rules approximately after filtering. What does rule filtering involve? Well, we don't want redundant rules where the antecedent and consequent encompass one another, such as if pass incomplete, then no yards gained. We also don't want ineffective rules. It's already known that football teams tend to pass in long yardage to their down situations, so this isn't helpful either. Good rules tell us something about the outcome of the play, such as whether an opposing offense is going to run or pass the ball, or whether an opposing defense is going to blitz. In conclusion, the purpose of this project is to generate meaningful play calling tendencies that can be used to help with game planning or self-scouting. Our project also addresses the issue of adapting existing algorithms to work with real-world data with dependent features. Future work for our project can involve visualizing our findings and connecting rules and patterns with film. Thank you for your time.
Hi everyone, my name is Sarah Kishta, and the project that I'm working on is STEM Illinois Noble Project, Youth Health Data Analysis. A quick background on me: I am a senior majoring in community health at UIUC. My graduation date is May 2022, and my mentor for this project is Dr. Ruby Mendenhall. I will be participating in building a cohort of youth community workers to analyze the situation of African American community during COVID-19 time and how it affected them. The goals for this project is to provide underserved students and students of color unprecedented access to resources at the University of Illinois Urbana-Champaign. We are going to create a pilot community health worker program with high school students in Champaign-Urbana, Chicago, and Pembroke. Our long-term goal for the project is to create 100,000 community health workers. So community health workers are people who serve as a bridge between the community and health services. Community health workers are important in terms of strengthening connections among community networks and connecting both health services and social services together. They facilitate access to health services for the community and improve the quality of cultural competence of service delivery. The program also builds individual and community capacity by increasing health knowledge and self-sufficiency through a range of activities such as outreach, community education, informal counseling, social support, and advocacy. From this graph, we could see the impact of COVID-19 on the communities of color. The most affected people by this is indigenous, Blacks, and Pacific Islander populations, and then followed by the Latinos, whites, and Asians. Indigenous, Black, and Pacific Islanders Americans have experienced the highest death toll from COVID-19. So, how we plan to implement our program, we're going to start off by training 4 initial health equity scholars for the community health program. These scholars will help in training 30 to 45 middle to high school students to become healthcare workers. Then students will take on and conduct research on the health condition in their community in terms of COVID-19. We will collaborate with Morehouse College of Medicine and the Illinois Community Health Worker Association. We plan to reach out to the CUPHD to discuss possible collaborations. Thank you so much for your time.